Okay, I think we can get started. Well, good morning, everyone. My name is Yan. I'm a senior associate at ADL Ventures. Thank you for taking your time to join today's discussion around thin-film solar reliability. Thin-film solar technology, especially some of the emerging technology like perovskite solar cells, have demonstrated very competitive efficiencies with potential for even higher performance. But as many of you here today know, stability or reliability of those solar cells is still quite limited. And that limitation is something that technology developers need to address in order to position those new PV technologies as competitive commercial products in the market. That's why today we invited 3 domain experts in thin-film solar and solar reliability to share their experience on how to prove the long-term reliability of thin-film solar technology to stakeholders. Today's event is a collaborative effort with DOE Solar Energy Technology Office and NREL. Before I move on to today's event agenda and speaker introduction, Peter or David, do you want to give a few words to the group?
Yeah, thanks, Jen. So I just wanted to welcome everybody. My name is Peter Lubicaro. I'm from the Solar Energy Technologies Office from the Manufacturing and Competitiveness team. We are the team that's sponsoring the Perovskite Startup Prize, and this webinar is being given in relationship to that prize competition. We're very excited to have you all here, and we hope that you will find the things that are presented here today interesting and compelling, and hopefully concepts that you can bake into the work that you're doing, the technologies you're developing, whether they be in the lab or in the commercial footing. So I think that's all I want to say for now, Yan, and why don't we move right along?
Great, thank you, Peter. Okay, so today's event will be a mix of webinar and panel discussion. During the first half an hour, 2 of our speakers will present on how they tested and demonstrated thin-film PV reliability and bankability. After that, we're going to have a panel discussion with all the speakers to dive a little bit deeper into different types of conditions, standards, and other factors that should be considered when doing reliability testing. The last 10 to 15 minutes will open up for Q&A, but you don't have to wait until then to send in your questions. I suggest, whenever you have a question, just post them into the Q&A section during the event. One last note, the webinar section will be recorded, but the panel discussion part and the Q&A section will not be recorded. With that, I'm going to move on to the speaker introduction. Oops. Sorry. Okay, so our first speaker today will be Dr. Eric Lee, who has been involved in the solar industry since 2008. He was in charge of product development at Solo Power, where his team produced the industry's first flexible 6 module. More recently, Eric ran the R&D team at Styon, developing cell technology for 6 and tandem perovskites. Currently, he's working at a small battery company in the Bay Area. And our second speaker will be Dr. Alan Ward, who is a PV scientist and technology manager at DOE Solar Energy Technology Office, working as a member of the photovoltaic team since May 2020. He currently supports PV development projects focused on innovation in materials and designs for low cost and high reliability at both the module and system level of integration. He's also co-managing perovskite PV cell and manufacturing technology projects with an emphasis on performance validation and bankability. Before joining Solar Energy Technology Office, Alan was a scientific fellow and technology director at First Solar, working in the areas of CAD cell module and system reliability and advanced module materials and designs. And our last speaker today is Dr. Ingrid Reppens, who is a research fellow active in the photovoltaic reliability group at NREL. She has worked for more than 20 years in photovoltaics, including reliability, device processing, characterization, and manufacturing. She brings an in-depth understanding of material science and device physics to high-impact questions about reliability and product life. I'm very excited about the diverse experience and our speaker bringing to the table today. And with no further ado, I'm gonna hand it over to Eric, who's gonna share a little bit about his experience with reliability and bankability on the 6 module side.
Thank you. Thank you, Yan.
No problem.
So today I'm going to show you 4 slides. The first one is an overview of reliability testing for product development, certification, and bankability. Product development reliability becomes critically important as you approach commercialization. However, it's still important to do it at early times just to make sure you don't get locked into a material set or a process that isn't extendable to an actual product. Certification, so UL certification, it's a safety test. You have to do this before you can connect to the grid. Your customers, if you have customers, they're going to want you to be bankable. And bankability is your UL IEC certification plus a couple of years of field data plus a bankability report. Then the next 2 slides, I'm going to show you a reliability testing plan that I've used in the past, and then also a schedule, again from one of my previous previous companies. And this isn't to say that these are the perfect way to do it, but these are just 2 examples of how it's been done in the past. And then lastly, I'll talk a little bit about sample quantity. So reliability testing for product development. If you are an early stage company, let's say you're existing on angel money, you're in an accelerator, you're on R&D money, or maybe even you're on Series A, really what you need to do is produce a couple of cells that demonstrate your concept. As you get further along in the product development process, you'll start to focus less on the successes and more on the failures. And when you're finally shipping product to customers, that's what you care about, is fixing all the problems. Now, in early product development, you need to understand, still need to be testing for 1 or 2 things. And if you're in perovskites, maybe what you're concerned about is stability under light soak. So you should start early and often testing for those 1 or 2 key reliability failures. Nothing sinks a small company faster than poor reliability. I have some examples of work that I've done in the past. And this is one of our first modules we made with the new interconnection process. And as you can see, it's important to test early to see what the problems are. I got to say, the one good thing about reliability testing is you occasionally get very catastrophic and charismatic failures. Certification. So UL certification means that your module will not cause a safety problem when it's connected to the grid. And the requirements for certification are well defined and well understood by almost everybody in the industry. You need certification if you're going to connect to the grid, as I said. And once you have it, this means you can start sampling products to customers. It also means that you can start putting your own product out into test fields. So you can start your own long-term field testing. And this is also a time for you to reach out to NREL and see what recommendations they may have for long-term field testing. And lastly, certification is generally a requirement from investors. For customers, customers really want bankability. Bankability is what the banks require, the investors. The bank may actually be Wells Fargo Bank, but it could be a specialized clean tech investor. Your customer, if you're making modules, is going to be a developer. The developer has to go to the bank and get financing for the project that he's doing, he or she is doing. And this comes in the form of a bankability report. Part of this report, they'll want to see several years of field testing. And then on On top of that, the third-party test house that's doing the bankability report will likely have a few more laboratory tests or chamber tests that they'd like to do. And common third-party test houses that make up bankability reports are RETC, PVEL, and Intertech. Usually the cadence of a company is that it will go through a product development cycle, get up to series C, and have a product that's ready for certification. It'll certify and make enough modules that it can start doing some outdoor testing, and then go back and raise enough money to put in a manufacturing line. This will be $30 to $50 million. And it takes a couple of years for that line to get up and running. And so hopefully by the time that you're prepared to ship large amounts of material, you'll have a year or two of field data that you can show customers, plus you'll have your certification. Often your module has changed in those 2 years. You've made improvements to it, so you may have to go back and recertify, but still the banks will look favorably upon a couple of years of field data for your previous model. One question that often comes up when people are in the product development process is, should they certify a demonstration module before they're ready for production? And especially with perovskite companies, a lot of them have a business model where they're not actually making modules. Instead, they're going to make cells, and then they're going to sell to the module manufacturer. So there are pros and cons of you doing a certification yourself. The pros are it looks good to your investors. And the other pro is it looks good to any cell customer if you can show that, in fact, you are able to certify. The cons are it costs money. And the second con is it takes time and attention to build a module. And it's all very doable, but still you're going to have to hire people, you're going to have to hire the modulating equipment, and that can get expensive. Now, I note that there are module design houses, for example, D2 Solar, that will do all this as a service. And again, it costs money, but it's probably going to be cheaper than if you were to invest in modulating equipment yourself. Okay. Here is a certification plan that I've used in a previous company. And this is a rather extensive plan. It covers both the UL requirements and then a few other internal requirements that are more like what you'd see in a bankability test. In this test plan, I've listed here the certification requirements, and then also what we would like to see internally for our product. And then some idea of the amount of time and the success criteria. And then finally, how many modules you're going to need to conduct these tests. And then you roll it up, and this takes about 100 modules. One thing I would say to small companies is it's good to have a full plan in your pocket. Maybe you don't do everything right away, but you want to have something that you show to the board because you're gonna need resources for this. You're gonna need money. You're gonna have to buy chambers and things like that. So make up a certification plan and make sure that the board is aware of it and when you're gonna have to spend tranches of money to accomplish this plan. Schedules. Also, you need a schedule. If you're the project leader or the chief executive of your company, it's your responsibility to make a schedule. You need to go to the engineers involved and get them to tell you how long different things will take. But understand that as the leader of that project, you're responsible for the schedule. A good researcher is generally a bad scheduler. They're going to give you a timeline that's just way too optimistic. So you have to do some common sense assessment, take what they tell you and do some common sense assessment over how long it's actually going to take. One problem that I've seen with schedules is that people tend to do one best case scenario after another, and they say, okay, in 2 years we're going to be here. Problems happen. Not everything goes according to schedule, and yet it's hard to throw in just a sandbag, say, add filler to your schedule. What I recommend you do is you add a learning cycle. So after you've done a few experiments, then you expect to have 1 or 2 learning cycles. And this says that, okay, you don't know exactly what you're going to be doing, but presumably you've learned something over these last 2 months and you're going to apply that. Plus, it gives you an opportunity to catch up if for some reason you fall behind. And the other thing I would say to a small company is you should use your schedule. Often a schedule is made up, it's shown to the board and then forgotten. I think it's important to every week or maybe every month, you check back where you are in terms of that schedule, just to see if you're on track or not on track. Now, this particular schedule, we start with making mini modules and trying out a few different build of materials. This is material sets for the module. This assumes that you've got a cell and you're starting to package it. And we spend several months working with small samples until we're in a position to say that, okay, this one set of materials are good. And then we can go back and do a fuller set of experiments on mini modules with those 2 bombs. And then we can go to full-size modules and start filling out the test requirements with the full-size modules. And from here, it looks like it will take a little bit over a year or so to have your module internally certified. And if you're in a big hurry, you could maybe start the certification process before it's internally certified. Although, of course, it's better to wait until you're internally certified and then start your third-party certification testing. So from starting your packaging experiments to a finished certified cell, it's probably going to take you a year and a half. Sample quantity. Let me tell you 2 ways that people determine sample quantity, and then I'll give you my recommendation. Often, and if you look in the UL standards, they say 3 modules per test. And this is generally because if one goes bad, 2 are still good. You can say, well, it's just that one module that went bad. The proper way to determine sample size is to look at the variation within your production, which is to say the standard deviation, and then look at the smallest change you want to be able to resolve. And then using those 2 factors, you can, there are several sample quantity calculators that you can use on the internet. And also if you're using JUMP or some other statistical software package, they have pull down menus that using the standard deviation and the smallest change, they'll give you a sample number. Here I have a recent example that I've done with this is with a battery cell. This is some normal production, which when you histogram it, gives you some idea of what your average is and what your standard deviation is. If you plug this number in the standard deviation into a sample size generator, for example, in JUMP, for these 3 different standard deviations, and for these 3 different resolutions, you can get sample sizes that range from 99 samples down to 3 samples. If you're a small company, you're going to be resource constrained. There's just no way you're going to be making 99 samples. And even 9 samples is going to be tough to do. So my recommendation to you is that learn what your standard deviation is. And then you can plug that standard deviation into the sample cell calculator, and it will tell you how big of a difference you can resolve. So start with the number of panels or the number of samples you're willing to make, and use that to see the resolution of the experiment. So my practical advice is to start with at least 3 samples and use JUMP to work up the data. So 3 samples and using Excel is probably not a good idea. You want to use a proper statistical analysis program such as JUMP, and it will do all the statistics in the background for you and tell you if, in fact, you've used enough samples to be able to resolve the difference that you want. Now, I want to make one final plea to all the small companies out there. Please take a look at your process control. Usually, statistical process control is something that a manufacturing team looks at, but even a laboratory operation, it's important to understand how the limits to your process. For example, if you're using an oven, make sure that all the spaces in the oven have the same temperature. Or if you're coating, check the uniformity of your coating. And if something is off, take aggressive action to fix it. It's important in the laboratory when you're making samples that you have tight control over your process. The phrase that people use is build in quality versus test out bad cells. So it's not that you want to just make what you make and then in the end test the bad stuff. Instead, every step of the way, you want to try to be making good material. So that's my plea to all the small companies out there. And I think I've reached the end of my time and the end of my talk.
Thank you, Eric. That was very insightful and helpful. So now I'm going to pass it on to you, Alan, to share some of your perspective from the CATL technology angle.
Thank you, Jan. Thank you, Eric. I thought that was a great presentation. I'll be talking about what I learned during my experience working at First Solar from 2010 to 2020. And I had the good fortune to join the company just as they were starting to get into truly high volume ramp up. And so I wanted to share some of my experiences, and hopefully you can consider some of the things I learned and try to apply it to your endeavor. I'll start by talking about just a brief background on First Solar's CATL PV modules, and then I'll give some anecdotes and some discussion around testing beyond the reliability standards. This isn't meant to be a terribly technical presentation, but more sharing my experiences and perhaps offering some guidance. I'll make a special point about warranty and liability claim preparation. I found that to be very key to success. And then some final thoughts to consider, particularly on standardized testing. So for First Solar, their high volume ramp up started in around 2007. And at the time I joined the company, their total fleet size was 1 gigawatt. So they had been producing several hundred megawatts for a few years. And between 2010 and 2020, my tenure, there were at least 8 major technology changes during that time. So that works out to about 15 significant technology changes per year. And First Solar offered these technology changes in the forms of bundles. And so there were always several R&D projects going on at both the cell and the process design and the packaging levels. And as those different sub-projects became ready for prime time, they got bundled and qualified together and released. And so it was really a matter of working on multiple things in parallel as opposed to a serial technology advance. And what I'm showing here, when I joined, the Series 3 was in production. That changed to the Series 4 with essentially the same form factor. And there was an effort to make a Series 5 that I've shown here, where since the module was frameless and the company realized they were paying a pretty significant penalty at the balance of systems because of all the extra connections, both mechanical and electrical, for a small size module. They wanted to go to a larger module. And the first proposal was to mount the modules, pre-mount them on a rail with wire management. But ultimately, it was decided that a better approach would be to go ahead and make a larger module that also allowed incorporation of some process advancements that had been made, and in fact, an entire retooling of the factory to get them up to where they wanted to be in terms of all the prior learnings. And so currently, their product is a Series 6 copper reduced module, which gives it better stability. You can see that they've added a frame and some more advanced wire management. And the form factor has gone all the way up to 2 meters to approximately 1.2 meters in size. First Solar currently produces over 5 gigawatts per year. In fact, I think it's over 6 gigawatts per year production capacity now, with a total fleet size of greater than 25 gigawatts. And I mentioned this simply to point out that First Solar PV success is possible. And the way they got there was to focus on continuous improvement in all aspects of the business. So one thing that I found important and integral to both the research and development efforts and their continuous improvement efforts was the investment that was made in reliability assurance. And when I say investment, I mean both in the facilities, the equipment, and the people. In particular, with new cell technologies, it's very important to understand all aspects of the cell operation and test it in as many different ways as you can. And so my first bullet of advice is cell performance and stability should be studied in all modes of operation. We found different reliability behaviors in open circuit, maximum power point, short circuit, reverse bias, undershadowing, in dark storage, which is meant to simulate the time a module might spend in a container, perhaps sitting on an ocean-going vessel or sitting in the desert for weeks on end. And then both in accelerated and field test modes, we found unique behaviors in all of those modes. So it's important to test all aspects of device operation. One thing that I believe to be true is that most of the historical CAD/TEL field issues were from the package and not the cells. However, customers really don't make a distinction. It could be a package failure that has nothing to do with your cell technology, but if you're in the perovskite business, they'll call it a perovskite failure. So from that perspective, it's equally important to pay attention to cell and package reliability. And then beyond that, most historical CAD/TEL field issues are quality related and not intrinsic materials or design related. I think that's in part due to the good upfront work that was done on the intrinsic materials and design. And it's not to say that the quality is bad. In fact, CAD/TEL field quality is quite good. But if there is a failure, it's generally due to some sort of either quality in assembly or installation in the field. What I can say with great certainty is that in my experience, almost every change to the materials, design, or process of semiconductors or packages results in measurable change in reliability behavior. And I say that not only from the perspective of CAD/TEL PV modules, I also worked in wide bandgap semiconductors for 10 years and in AlGaAs HBTs for telecommunications for 5 years before that. And in every case, I think this holds true. My overarching message is that it takes a lot of resources to do a good job with reliability, human, equipment, and facilities. And so managing those resources is key, especially for a young company that really doesn't have a lot of extra money to put on these types of endeavors. And so one bit of advice is that customers that really deep dive into reliability and durability, that may be a sign that they're actually risk averse. And they only commit to purchases after several gigawatts of your product have been problem-free for several years. I can't name names, but we experienced a lot of resource allocation to companies that ended up never buying anything, or at least not buying anything for several years. So consider focusing on the big fish, so to speak, only after high volume generation product is bankable. But also consider the minimum size of your small fish. So it would be better, for example, to have 2 customers that are offering 100 megawatt opportunities each than 20 customers offering 10 megawatts, simply because it'll spread your resources too thin. And final bit of advice on this point is that customers who do accept early adopter risk I found generally want to see about a megawatt of fielded product performed for about a year for bankability purposes. The reason for a year is it gives you exposure to all seasons of the year, and for quite a number of reasons, different types of metastabilities behave differently as a function of season, and so they want to see that. And then a megawatt, 1 to 1.5 megawatts is about a block size, and so that's a common pixel size for a lot of utility scale facilities. So thoughts on certification and safety testing. Yes, you need to pass the IEC and UL PV durability and safety tests, whether they're relevant to your technology or not. With CAD-TEL, especially in the earlier years, we were subject to the silicon IEC and UL tests, which weren't necessarily relevant to what we were doing. And don't make the mistake I did trying to convince people that those tests weren't necessary. You'll be expected to pass the test anyway. Outside test labs are generally more trusted by customers in executing IEC and UL tests. You should, as Eric mentioned, do them yourself and make sure that you can pass before getting certification in an outside lab. But you will need to do that because the customers will trust those outside entities as objective arbiters. You do need to provide resources, however, to those labs and work with them so that they properly configure the tests for your technology. They can learn the nuances of your technology and properly interpret test results. So again, it does take quite a bit of people from your company interacting with those outside test labs to be successful. Minimize your quality-driven reliability and safety risks by using sampled product for ongoing certification and safety testing. And so what I mean by that is quality-driven reliability is when there is some sort of quality defect that ultimately results in the degradation or failure of your product. One thing that the certification tests are especially good at is detecting those early failures. And so one strategy to consider would be to use those IEC tests, and this does not have to be customer facing, but simply an internal exercise to periodically sample your production and make sure you pass those tests. It was surprising how often those types of tests caught deviations in quality from production. And my final bit of advice is that the national labs, particularly NREL and Sandia National Lab, can provide crucial photovoltaic lab expertise, field test resources, and credibility to qualification. Many customers and independent engineers will seek national lab opinion and guidance anyway, so it's always good to develop the relationships and work with them early on. I thank you for your attention and wish you good luck in your future endeavors. Back to you, Jan.
Thank you, Alan. And also thank you, Eric, again for sharing your experience and knowledge on thin-film solar reliability testing. So now I'm actually gonna stop recording. And